This video is to help you a little bit with the intermediate value theorem and maybe some of the problems that you're going to see in Newton as you go throughout section 2.4b. So here is an example of one that you might see. It says the intermediate value theorem guarantees that 2x minus sine x plus cosine x equals -1 has a solution over the interval -1 to 2. So what we want to do is think about what the intermediate value theorem tells us. If z is a y value between f of a and f of b. So what's really important is to note the relationship between a and f of a. So f of a and f of b are both y values, and that would make a and b x values. So z is a y value between these two. If the intermediate value theorem holds, it says that there will be an x value, c, between a and b. So that can be really hard to visualize if you're only looking at equations and words. So in order to kind of look at this problem, there's two things we need to do first. We want to change our equation to function notation. So let's begin by moving this 1 over here to the other side. That would give us 2x minus sine x plus cosine x plus 1. And we want to know what this thing equals, so we're going to let it equal f of x. Okay, that's just a fancy way of saying y. Now, notice that in our problem, the z value we desire is 0. And how do we know? Well, if you think about what it means to have a solution, right? It has a solution means find the x value that makes the equation equal to 0. Well, I think it would really benefit you if you took a look at maybe what this thing looks like in a graph. So I'm going to go to this website, Desmos. It's fairly useful, and we're going to do the graphing calculator. Give me just a minute to let this thing load up here. So Desmos will help us visualize what our graph looks like. And once we visualize that, I think it'll make sense what we're looking for in terms of the intermediate value theorem. So our function was 2x minus sine x plus cosine x plus 1. 2x minus sine x plus cosine x plus 1. I always like to double check to make sure my values are correct here. And again, we wanted to know, is there a 0 on the interval from -1 to 2? Okay, so -1, if you look right here, -1, let's see if I can move that point right, there's -1 right there. And you'll notice that y value is positive, 0.382. And then over here to 2, again, you'll notice at 2, the y value is positive. And what's more important is that between -1 and 2, this graph does not cross the x-axis. See, this right here would be a solution, -1.158, because the y value there is 0. So that makes that a solution. But in our problem, we've got two positive values. So let me give you sort of what the intermediate value theorem would tell us here. If our interval went from -2 to +2, okay, so -2 is here, okay, and +2 is up to here. The intermediate value theorem says that because one of these values is negative and one of these values is positive, there has to be a place where the graph crosses the x-axis. So we can see, again, at f of -2, the y value is negative, and at f of 2, the y value is positive. Because there's one value that's negative and one value that's positive, we can guarantee that between -2 and 2, this graph has to cross the x-axis. So how would we do that analytically if we're looking at our equation? Well, our job is to show that f of a and f of b have opposite signs. In other words, f of a is below the x-axis and f of b is above. Because in order to connect those two dots, I have to cross the x-axis at least once, and that would be the solution. So what would happen if f of a and f of b are both positive? Okay, both positive. Well, that would look like this. And it's possible for me to connect those dots so that the graph never crosses the x-axis. It could do like this, but I don't know that for certain. And so the intermediate value theorem says that because these are both positive, we cannot guarantee that there are solutions between -1 and 2, okay? So if they have opposite signs, yes, we can guarantee that. If they have the same sign, if they're both positive, or let's say they were both negative, I would not be able to guarantee that. So here's what we're going to do. We're going to find out what f of a is. We're going to plug in -1 to our equation up here. So f of -1 is equal to 2 times -1 minus sine of -1 plus cosine of -1 plus 1. Now there were some trig identities that were used in Newton, and so if you didn't quite understand what they were doing with those values in Newton, I'll show you how we can do this without changing that around. So again, Newton will change the signs here of a couple of these, and it can throw you off. So I'm going to go to my calculator, and I want to find out what the sine of 1 is. There's my calculator. I'm going to be in radian mode, and I'm going to hit -1 sine. So you can see the value of sine -1 is -0.84147. 84147, okay? I'm going to do the same thing for -1, but I'm plugging that into cosine, and that's 0.5403. 5403. So now when I combine all of these values together, okay, we'll work that through on the calculator. I'm going to have a -2, and it winds up being a positive 0.84147. Again, it's positive because those two negatives are side by side. Now I'm going to add 0.5403, and then I'll add 1. And the value of -1, f of -1 is 0.38177. What's most important here is that it is a positive. It's a positive 0.38177. Again, in order for the intermediate value theorem, in order for this to be a true statement, we need our signs to be opposite, okay? So we're going to plug in +2 this time. So we'll go in, again, f of -1 is 0.38177. Let's go in and plug in our +2. So this would be 2 times 2 minus sine of 2 plus cosine of 2 plus 1. If you're wondering where the 2 and the -1 come from, it's right up here in our interval, our original problem there. So I'll grab my calculator again. This will be 4 minus the sine of 2. So 2 sine equals, okay, so this is 4 minus the sine of 2. Now I'm going to add in the cosine of 2, and then I'm going to add 1. And I get 3.67. So it's not really important exactly what that value is, more so than this value is greater than 0 and this value is greater than 0. So because they are both greater than 0, this is false. I cannot guarantee that this thing will actually cross the x-axis. There's another intermediate value theorem problem down here. This one says find the smallest integer such that the intermediate value theorem guarantees a 0. So I've got 2 and a, okay, 2 and a. I want to be able to guarantee that there is a 0 between 2 and a. So here's what must be true. If this is my x value of 2, then my y value would need to be here, okay, and that a value A is here, that A value would need to be somewhere right in there, maybe a negative value. So in order to figure out what the boundaries are, okay, in order to figure out what these boundaries are, I want to know, where does this thing actually cross the x-axis? Okay, where does it actually cross? I know it's going to cross twice because there's a 2 right here, but where does that happen? If I can find where it actually crosses, I will know what value to assign A. Let's figure out where this thing crosses. So I'm going to set this equation equal to 0. When I do that, I create something that I can use the quadratic formula. So -4 plus or minus the square root of b squared minus 4 times a times c, all over 2a. Okay, so again, you've seen this before and it's been a while, and you know, sometimes these Newton problems can get a little bit difficult. So this will be 16. When you multiply these 3 negatives together, you get a negative result, and this is all over -2. 16 minus 4 is 12. So one of the values that I'm looking at is going to be -4 plus the square root of 12 all over -2. And the other value is going to be -4 minus the square root of 12 all over -2. So let's see what we wind up with as we work through these on the calculator here. Again, these are very calculator sensitive. So I'm going to take the square root of 12 and I'm going to assign it a positive value because I'm going to do -4 plus the square root of 12. So doing -4 plus the square root of 12 is the same as doing the square root of 12 minus 4. Now we have to divide this by a -2, and the result here is 0.268. All right, so x is equal to 0.268. And the problem with that is that this is outside the boundaries of what I'm looking at, right? My x values begin at 2, and that number is actually over here. So now I'm going to do -4 minus the square root of -12. Okay? -4 minus the square root of 12. So on my calculator, I've got a -4, and I'm going to subtract out the square root of 12, and then I'm going to divide that by -2. And the other value here that I'm dealing with is, 3.73. Now let's read the question here. It says, find the smallest integer such that the intermediate value theorem guarantees there is a 0. Well, I know there is a 0 here at 3.73. So this smallest integer value would have to be 4. So let's take a look at what this looks like on the graph. Again, -x squared plus 4x minus 1. -x squared plus 4x minus 1 looks like this. Here is 2, and so the y value of 2 is there. 4 has a y value down here that is negative, and notice these are opposite, right? One's positive and one's negative. And the intermediate value theorem does work here. It guarantees there is a 0 between 2 and 4. In fact, that 0 is 3.73. Okay, so the answer to your problem is 4, but we're using this to make that determination. I hope this helped with the intermediate value theorem. If it didn't, please give me some feedback, and I'll be glad to provide you with some additional resources.